Okay, so now we're up to our special cases. And I see my glare is kind of seeping through a little bit more here. So hopefully you're doing all right. Okay, I realized I wrote this part first, and then I wrote in this side. Don't know why. I'm a lefty. I do a lot of things backwards. I read magazines backwards, things like that. And so then I realized that I had a few more examples here that I would love to include. So if you're gonna pause the video and write everything, leave a gap between here and here so that I can do these four. I'll erase them, I'll add my last pieces of it, my last few examples, and then we'll go into here on this left hand or this right hand side. All right. So special cases, some good easy pieces, always some tricks to go along with it. So I don't know if you recall when we did the foiling, whenever there was a problem where these were the same and the back was the same and we had one positive factor and one negative factor, our middle guy dropped out. For instance, so just off to the side here, if I have x plus 2, and I have x minus 2, I'm already writing the answer. If I try to FOIL that, I would end up with x squared minus 2x plus 2x minus 4. And the middle guys ended up dropping out, so we had x squared minus 4. So now we're going to start here, and we're going to move backwards. And notice that the thing that makes this the most interesting is that there's only two terms. There is no middle because the middle dropped out. Another equally interesting thing is that we have perfect squares. 4 is a perfect square, it's 2 times 2. X is a perfect square, it's x times x. So this is yet another type of factoring that we will use when we have a perfect square in the front, a perfect square in the back, and a subtraction sign between them, meaning difference. The difference of two perfect squares. I would highly, side comment, I would highly recommend that you know your perfect squares through 12 times 12 is 144. If you know all the way through 20 times 20 is 400, obviously you can still use your technology, but that number recognition is going to be critical, and it becomes a lot easier when you recognize those number patterns. So for instance, if I throw up 64, that you automatically think, oh, that's 8 times 8. Or if you see 36 and you go, oh, I know that's a perfect square, it's 6 times 6. So that's the type of number recognition I'm talking about. And I specifically chose ones that I know I don't already have up here on the board. Okay, so I see that I have x squared minus 16. That's a perfect square. 16 is 4 times 4. So when I go to break this apart, I want that middle term to drop away because I want it to add up to 0. So if we're going to make it fall into the same pattern as 5.2, we want that middle term to be 0 x's. We want it to go away. So two numbers that multiply to 16 and add up to 0 is x plus 4 and x minus 4. So you basically just take the square root of the first and the square root of the back and plop them in their spots. The square root of x squared is x and x. The square root of 16 is 4 and 4, and 1 positive and 1 negative. So a lot of different ways to think through the same exact type of problem. Let's look at B. B varies just a little bit because instead of x squared, I wrote a larger exponent, x to the 6th. When you're given a problem that has a larger exponent than just that 2, just take that exponent and divide it by 2. So this is x to the third squared, or x to the third multiplied by x to the third, because when we square an exponent, or when we have an exponent raised to an exponent, we multiply. So when I split this up, and I take the square root of the number in the front, or what multiplied by itself is going to give me x to the sixth, the answer to that is x to the third. What is the square root of 25? 5 and 5. 1's going to be positive, and 1's going to be negative. Let's go with another one. Here we have a problem that doesn't come in descending order. So a few videos ago I said you always want to put these in descending order until you don't. And so this one, because it falls into this perfect square, 1 is a perfect square, it's 1 times 1. 9 and y squared are perfect squares, 3y times 3y. So it's okay that this one isn't written in that descending order. Square root the first number, square root this number, or that term, I guess I should say, and 1 is positive and 1 is negative. I always write the positive one first. It doesn't matter. It's just what I've always been in the habit of doing. All right, this one right here, each one of these kind of just has a different trick. So you can go back and forth on the video depending on what you think is the level of difficulty. Maybe this one to you won't be as hard as that one was. All right, so here we square root. We notice it falls into the pattern. Perfect square, perfect square. Whenever this exponent is even and the coefficient in front of it is also a perfect square, then we know it's going to fall into this pattern. So if we take that 4 and divide it by 2, this right here, when I square root it, we revisit this concept again in chapter 10. But this is y squared squared, because 2 times 2 is going to bring us back to y to the fourth. So square root, or divide by 2, this first term, and we get y squared and y squared. If I square root 16, I get 4 and 4, and I have 1 positive and 1 negative. All right, what is interesting about these two factors? Well, this is still a perfect square. Y times y is y to the second power. 4 is still a perfect square, 2 times 2. And so one of these factors can be factored again, and it's not this one. This one just stops. You cannot continue to factor, and that's the next thing I'm going to put on the board. You can't factor if that's a plus. There is no trick for that. All right? But this one can be factored one more time. So this one is going to become y plus 2 and y minus 2, because the square root of 4 is 2. So my final answer, I have to rewrite this underneath itself so that all 3 factors line up. Let me circle this one. That is the final answer to the question in any order, okay? So, I do want to write that idea down right here. A squared plus b squared is prime. The only exception to that rule is if you can take out a GCF. But for all practical purposes, there's no little trick like the little formula or like those difference. If that is a plus, it's done. So if you are given a problem that looks like this, you write down prime. If you're given a problem that looks like this, you say, gosh, both of those are even, so I'm going to pull that 2 out, and I'm done. Because this point right here is now prime. The hardest type of problem with these perfect squares, the difference of 2 perfect squares might be something that looks like this. So let's just try one more. Let me think of one real quick. I just threw this out here. Let's do something like that. And once again, it's super similar to the one I already have up here. So as you approach this one, you might want to just pause and try. Try not to look back at your other examples. We're going to pull that 5 out front. We're going to get x to the 4th minus 16. The thing about 16 is when you square root it, the square root of 16 is 4, which is also another perfect square. So that's the one that's going to get you the most often. So we're going to have x squared and x squared. We're going to have plus 4 and minus 4. This is done. This piece is done. This piece can continue to x plus 2, x minus 2, and so then this part just gets rewritten, and that is your final answer. All right. One can be tricky also, so I'll do one more like this. One can also seem super tricky, because 1 times 1 is 1 for a really long time. So if I have x to the 8th minus 1, look at how long this is going to go on. We can divide that 8 by 2. And you don't have to write all these down, but it might be helpful. So this part is done. But this part can continue because 1 times 1 continues to be 1. And now this part is done, so it just comes straight down again. And this now is a plus, so it comes straight down again. But this can be broken down one last time. And now this is your final answer. And I think that is why when I factor these, I always write the plus term first, because then the first guy's always done, and I only ever have to ask myself, is the back term factorable again? And so it's just what I do to keep my stuff organized. All right. These are actually pretty quick and fun and easy when you get used to them. I mean, not like Friday night fun, but as far as math, it follows a really nice pattern. All right, perfect square trinomials I don't love. And if you are tired of learning one more pattern, one more thing, for most practical purposes, you don't have to put this into practice. I don't choose a lot of examples that use this. Here's why. You notice here that the first term in the problem is a perfect square. The last term in the problem is a perfect square. And so what this pattern is telling you, whether it's a positive here or a negative here, the only difference is that right there. What it's telling you is that if you just square root the front and square root the just rewrite it like that, and it's all wrapped up quick and easy. For instance, if you look at this one, if you square root the front term, x times x is x squared. If you square root the back term, 3 times 3 is 9. Everything is plus. So it wraps it up perfectly. Now, does it follow the pattern in this regard? And the answer for this one is yes, it does. So is this middle term 2 of these pieces multiplied together? So if I multiply x times 3 and double it, do I end up with this? 3 times 1x is 3, and then that, and then yes, it does. Now, if you're not careful, and again, if what this part of the lesson, if it's like, I am not understanding, it is okay, because you don't have to use this shortcut. It's supposed to be a shortcut, all right? So if we look at this one and you think to yourself, okay, well, I've got a perfect square in the front, and I've got a perfect square in the back, and so every time that happens, I'm just going to slap that up there, and so then this is going to be x plus 4 squared, but wait, because 4 times x, if I multiply these two pieces and double it, 4 times x is 4x times 2 is 8. Well, that's not 8x. So here's a perfect example where the first part is a perfect square, the back part is a perfect square, and it doesn't match the pattern. So not every problem falls into that category. So how would you do this? Well, you would solve this problem just like we did in section 5.2. You need two numbers that multiply to 16. Maybe you can't see this. I'm afraid I'm off the screen. You need two numbers that multiply to 16 and add up to 17. And the answer there would be 1 and 16. So this problem isn't even a perfect square trinomial, but yet sometimes we're misled when the first and the back are both perfect squares. Now, this does come in super handy in problems like this, where you maybe just get overwhelmed by how big all those numbers are. You can slip and slide this, all right? You can look at this question. Remember what I told you to do when you have two different variables. Just make sure that when you write your final answer, the x's go in the back. So when your final answer happens, you're just going to add an x into the back of each of those factors. And so as long as you remember that, you can do that, and suddenly that's a lot more manageable. Slip and slide it. Multiply. Two numbers that multiply to 36 and add up to a negative 12 is negative 6 and negative 6. If you multiplied by this 4 here, you need to divide by this 4 here. And so this reduces down to 3/2. Since I've already been through this lesson, I'm kind of just scribbling here. That 2 is going to slide out in front. And so this is going to give you 2p minus 3 and 2p minus 3. And don't forget that you have to put those x's in the back there. And if you wanted it to follow the pattern and write it really nicely, you could just write it like that. So that is an option that gets you out of ever learning this pattern. But if you say, gosh, I don't want to do all that work, so let's hope I remember what that original problem is. I have 4p squared, I already forgot it, minus 12 px plus 9x squared. Now, look at this same problem, and let's use this pattern right here. And I know there's a lot on the board, so I'm going to clean it up so we don't always lose track of where to look. All right, so this is a perfect square. This is a perfect square. So what is being squared? Well, this is 2p squared. And this one right here is 3x squared. And so according to this pattern, this shortcut, if you will, this idea of a perfect square trinomial, I can just write this and write that, and it's a negative, and I can jump straight to there. But we need to check that the middle term works. So the middle term has to be doubled when I multiply the two pieces of the factor. So if I multiply 2p times 3x and double it, do I end up with what my original middle term was? And the answer in this case is yes. 2 times 2 is 4, 4 times 3 is 12, and I have the p and the x. So totally your choice on this second half. If you like this shortcut, you're really good with numbers, you can see that and use it and implement that, that's great. If you're like, I don't need one more thing to learn, so I'm just gonna either use the slip and slide method or just kind of what we talked about in general in 5.2, do that and you'll eventually end up with the same answers anyways. So you are well over halfway through factoring, so well done. Keep up the good work, keep practicing. Hopefully you're practicing, maybe not daily, but hopefully you're looking at your math at least every other day so that you keep those skills up. Have a great rest of your day, class.